we're going to start out with a review of factoring on a higher level than you used to when you took an algebra course. And also, it's not, this particular section is not called simply factoring trinomials. It's also called factoring trinomials and special. Well, what does it say exactly? Factoring trinomials and special polynomials. You'll see what that means in a few moments. But the first question that I ask you to look at, it should be very familiar to you, because this question that I ask you is actually the last step of the difference quotient that we did on the exam. If you remember correctly, the problem, at the end of the problem, a lot of people didn't even get this far because there was so much algebra to deal with in the difference quotient problem that a lot of people made like little mistakes, so they wound up with all kinds of things. I won't go into all the things, but it's interesting how people could really botch up a problem. And you know that I've had my share of botching up of problems, so I know what it feels like. Even now, after doing math for all these years, I still botch up problems. But this is what you should have wound up with as a final step. And the way I showed you how to do this type of problem without having gone through this section on factoring was to take this problem and factor out an h. Because if there's two here, there's two here. In fact, let me just do it this way. See, this is what it really says. This is what h squared means. So you look at this and you say, okay, well, here's an h over here, and this term has an h. And we could take that, if the h is common in both terms, then that h can be pulled out of the binomial, put on the outside of the parentheses, and then inside is negative h, whatever is left over. And this is the first type of factoring called common monomial factoring. Common monomial factoring, or sometimes it's called greatest common factoring. The greatest common factor. And I'll tell you what that means in a moment. The concept of the greatest common factor, as opposed to simply taking out a common factor. But this is what you should have done on the exam if you got to this step. And then you would do this. And of course, the answer to this question was negative h plus 9. Or some students expressed it as 9 minus h, which would have been fine as well. So this is what we mean by common monomial factoring. Now, in this expression, well, let's start pretty basic. Take a number like 12 and think of all the numbers that go into 12. And if we think of all the numbers that go into 12, we can create a set. And it's just a question of going, from 1 to 12 and thinking of all the numbers that divide into 12. 1, 2, 3, 4. These are all numbers that divide into 12, 6, and 12. And this is called the set of factors. The set of factors of 12. And it's simply all the numbers that divide evenly into that number 12. Evenly meaning without a remainder. And if you have two numbers like 12 and let's say 18, and the factors of 18 are 1, 2, 3, 4 doesn't go in, but 6 goes in, and 18, of course, goes in. And you look at these two numbers, they have several common factors. forget it, common factors. These numbers that I'm circling are called the common factors. So the set of common factors is 1, 2, 3, and 6. And of those common factors, 6 becomes the greatest common factor. So this is all very, very basic stuff. GCF, the GCF, sometimes abbreviated as the GCF, greatest common factor. Okay, and this is what we're going to be doing. And in this binomial, the common factor is H, as it's not a question of greatest because it's the only factor of this binomial is H. Okay, so that's what we mean by a factor. Now, what I'd like you to do, just take some very, very basic problems and factor the following. Can we still see that? Yep. Factor. All right. So everybody in the class, kindly do the following problem. Okay, let's begin. Couldn't take it this long. This is the whole section on factoring is really serving as a tool for things we're going to be needing later on. We've used factoring already, especially as I indicated on the first test. So you look at this problem, and you can see that there's a couple of ways of doing it. For example, you could take out the 2 and say, okay, how about 4x plus 12? You could take out a 4, and you're left with 2x plus 6. And of course, you could take out an 8, and you're left with x plus 3. So in this situation, this would be the most correct solution to this problem. This is the greatest common factor. See, 2 is a common factor, 4 is a common factor, but the greatest common factor, the GCF, is the 8. And of course, to check it, you would simply use the distributive property and go 8 times x is 8x, and 8 times 3 is 24. Does anybody have a question? Okay, problem number 2. And you're looking at this problem and saying, okay, well, there's not much choice here, as there was in the first problem, because you must take out a common factor of 3, if possible, because 3 is the only number that's right there. So you've got to take out that, and you're left with x squared plus 4x plus 1, and that's it. There's not much more you can do in that situation, and that would be it. And then over here, well, the common factor is 5, and you get 2x plus 3y squared. So this is all pretty basic. Are there any questions about this? Any of these problems? Okay, let's get a little more difficult here. How about this problem? Okay, so first you try it, then we'll do it together. Well, you could do this problem by going like this. And simply saying, well, okay, common factor of x, common factor of x, common factor of another x, common factor of another x, common factor of the y. Common factor of a y, that's about it. You could take out x times y. And over here, you can't just put 0, it's not 0, it's 1 plus another x is still left over here, and 3 y's. And this is the answer. Well, this is not the answer, this is the answer. That's one way of doing the problem, just showing you exactly what's happening there. But that's not the way you should really get used to doing a problem. The way you should do the problem is to say, well, I have 2 x's here, 3 here, so I could take out a 2. And here I have a y to the first, and here I have a y to the fourth, so the largest common factor is y to the first, and then go 1 plus, and to get to 3 from 2, you would need an extra x, and to get from y to the first to y to the fourth, you would need 3 of them. And this is the faster way, obviously, of doing the problem, and this is the way you should get used to it, because we're going to be doing very, very, very complicated problems in section 3 and 4, especially chapter 3 and chapter 4, especially chapter 4, when we really get into some complicated problems. But this is an example of a little more involved kind of problem. Any questions so far? Anything on your mind that you're not sure about? This is it.
I have something I'm not really sure about.
Sure, go ahead.
So this is Rose.
Yes.
I put the answer as x squared y1 as the greatest common factor. In parentheses, I put x plus y3 instead of 1.
Well, that won't work. I mean, you could figure that out really for yourself by just simply going, if this was your answer, is this what you had?
Yes.
Well, what's x squared times x?
X to the third.
Yeah, but we only have x to the second.
Oh, okay.
Okay, so that's the way you check it. I mean, on your own, when I'm not around to answer the question, your way of checking it is to simply multiply using the distributive property, and you can see that this is not going to work. So therefore, we've got to change the x to a 1.
Okay.
All right. Anybody else? This is, I always like to start stuff really, really basic, as you know. And this is an opportunity to really ask questions, any question you want. Okay, next question. So we're building it up slowly, and this is the next question. Now, this is a very interesting question because this is a binomial to the second and a binomial really to the first. So, yeah, it's kind of a little more involved. And one way of doing this, of course, is to take x plus 2 and simply square it. And then see, how you can simplify the whole expression. But that's going to take a really long time. So the better way of doing this is to say, well, what does this mean? This means x plus 2 times x plus 2 minus 5 times x plus 2. That's what this really means. The x to the second, of course, can be written expanded like that. And the common factor is here and here. So you could take out the x plus 2 since that's the common factor, and then in brackets. Now, this is a reason to use brackets because here we're going to put x plus 2 that's still left over. See, remember we took out stuff and then there's always stuff left over. What's left over here is an x plus 2, but it's in parentheses. So keep it in parentheses, but then you want to not use more parentheses. You want to try something else that looks different. So this is called brackets. That's the purpose of using brackets. And then what's left here is just the 5. So this is what we're left with. But you want to simplify this even further, because here you can see you have stuff going on, and you would do this, and then you can get rid of the brackets by simply going x plus 2 minus 5, x plus 2 times x minus 3. Okay, so this is the better way of doing it. In other words, take out the common factor, you're left with this, then you could drop the parentheses and just put x plus 2 and then put the minus 5. And now you have to simplify. So a positive 2 and a negative 5 is a negative 3. And this is what it winds up being. This is a kind of an unusual problem, right? Okay, and we're going to keep going, actually. And if you think that was unusual, I'd like you to have a look at problem number 6. But first, make sure you can see it. Just take 12xy minus 3xb minus 8ay plus 2ab. There it is. Okay, now we're grouping them. Well, let's not even use parentheses. Let's group them just by simply going like this. That's the two groups. Now, the common factor here is 3x, because 3 goes into 12, 3 goes into 3, x goes into x. So we're left with 4y minus b. And then here we could take out the common factor of 2a, because 2 goes into 8, 2 goes into 2, a goes into a goes into a, very nice. Also take out the minus. This is what I didn't do before. Take out the minus, and you're left with 4y, right? Because 2 times 4 is 8, a times y is ay, and we can't leave this as positive. We have to make that negative, because this negative times that negative would make that positive. And then we've taken out a 2a, so what's left is the b. I hope you see what I just did. Once again, I'm actually factoring out the negative. There it is right there. And I'm factoring out a 2 from the 8 and the 2. I'm factoring out the a from the ay and the ab. So the negative 2a comes out, and what you're left with is 4y minus b. And now the common factor is 4y minus b times 3x minus 2a, excuse me. And this is the answer to the question. Now, you could see that there's all kinds of things going on here. There's a common factor of x to the third here and here, but over here also, actually. So that's good. And you could see that 5 goes into 35, 7 goes into 35. That's real nice also. But let's group it this way. Let's put this stuff together with this, because that you could see you could take out a 7, and that would leave you with, going, so just watch. So here's the factor of 3, and we're taking that out, and you're left with x to the 4th minus 5. Okay, so I'm just looking at right here, and you can see the 3 plus 4 is equal to 7, and you bring along the 3, everything is fine there. And over here, you could take out a 7, and you're left with x to the 4th minus 5. Okay, so let's go back. The common factor for these two terms would be x to the 3rd. And that works because 3 plus 4 is 7, and then 5 times x to the 3rd is 5x to the 3rd. Good. Now we go over here, and in these two terms, we could take out a 7, and you're left with x to the 4th minus 5. So that's good. That makes sense. Now, this is a common factor, and this is a common factor. So you could take out x to the 4th minus 5 times x to the 3rd plus 7. And that's the answer to the question. So I factored this into this into this. Then there was a common factor of x to the 4th minus 5. I pull that out. There it is right there. And what's left is the original x to the 3rd and the 7. And that's the answer to the question right there. Okay, that's completely exactly the way you would do that problem. This is a horse of a different color. Okay, that's pretty much greatest common factoring. And now we're going to move on to something else. And the first type of factoring was greatest common factoring. And we just did that pretty much. Now we're going to look at the next type of factoring. But before I actually state what it is, let me give you a problem to try. I'd like everybody in the class to do this problem. The multiplication of those two binomials. Just do that. So in other words, this is what I'm asking you to do. X times x is x squared. X times 4 is 4x. 3 times x is 3x. And 3 times 4 is 12. And you wind up with x squared plus 7x plus 12. Now, when you look at the answer, and you look at the original two binomials that you will multiply to get this final answer, this trinomial, you see a relationship among the numbers 3 and 4 and 7 and 12. These four numbers are all very, very closely related. Can somebody verbalize what's going on here?
I can. 3 plus 4 equals 7, and 3 times 4 equals 12.
It's good, exactly. So in this type of situation, and in this type of situation only, when there is no, when the coefficient of the lead term, the lead coefficient, that's called, this is called the lead coefficient. The lead coefficient. The numbers in front of the variable is called the coefficient. So this lead coefficient, the first one, is 1. When the lead coefficient is 1, it works that the sum of these two numbers equals the middle term, and the product of these two numbers equals the last term. So in other words, it's x squared plus the sum times x plus the product. For example, let's now go backwards, and here is, this will be problem 1, this will be problem 2. Here's x squared minus 10x plus 21. Okay, so I'd like you to look at this and see if you could factor it. Now, let's assume that this is going to work out to a product of two binomials. Now, what are the factors? What are the two numbers that multiply to give you 21? Now, it could be 21 and 1, or it could be 7 and 3. But remember that we need a middle term of negative 10. So the question is, which of these two possibilities gives us a 10? And you can see that it's going to be the 7 and the 3. Because 7 times 3 is 21, and 7 plus 3 is 10. So that works really well. The only problem is we have a positive here and a negative here. Now remember, this number is gotten by multiplying these two. And this number is gotten by adding these two numbers. And the only way of getting a positive 21 when you multiply and a negative when you add is to make both of these negative. And that would be the answer right here. So once again, negative 3 times negative 7 is positive 21, and negative 3 plus negative 7 is negative 10. Okay? Obviously, what we're doing is we're factoring trinomials, trinomial factoring. That's the second type of factoring. And in fact, here is a third problem for you to try in the same genre as the first two. So everybody in the class, please do this problem. Well, there's a lot of possibilities here. There's only one answer, but there's a few possibilities because the factors of 20 could be 20 and 1, 5 and 4. That's all 10 and 2, right? Those are all the possibilities, but we want the possibility that will give us an 8 somehow by either adding them or subtracting them. We want it to come out to be an 8. And the only possibility would be the 10 and the 2. So 2 times 10 will equal 20, and we have to get this combination to equal a positive. So obviously, this has to be positive, and this has to be negative. Because then, negative 2 times positive 10 is negative 20, and negative 2 plus positive 10 is positive 8. So this would be the answer to the question. But things don't always stay so simple. Unfortunately, you're going to get problems that look like this. And it's still going to be the product of two binomials. Now, but you have something else you have to think about because the lead coefficient is no longer 1. So you have to take into account that in order to get a 2x squared, you need a 2x here and an x here. And the only factors of 3 are 3 and 1. So you have to now think about how you're going to position the 3 and the 1. For example, you can't put the 3 here and the 1 there, because even though 1 times 3 will equal 3, when you multiply the middle terms together, there's no combination of 1x and 6x that'll give us a positive 1 in the middle. So there's, by putting the 3 there and the 1 there, that's not going to work because that's going to give you a 6x and a 1x. So that's no good. Even if you make this a negative, it's just not going to come out to a 1 using 1 and 6. So that's not going to work. So what you need to do is change the position of the 1 and the 3 so that the 3 goes here and the 1 goes there. And now you can see that 2x times x is 2x squared. Great. 3 times 1 can be 3. And now watch this. The 2x times the 1 is 2x. The 3 times the x is 3x. Can that give us a 1x? Absolutely. And in fact, we want it to be a positive. So what has to happen? This has to be positive, and this has to be negative. So in order to get, so the 3 has to be positive, and therefore the 1 times 2x has to be negative. And this is the answer to the question, because 2x times x is 2x squared. 3 times negative 1 is negative 3. That's good, right? But the middle term is the problem because now 3 times x is 3x and negative 2x. And when you add them, you get that expression. So that'll work out. And this is the answer to the question. You're going to have to come to grips with trinomial factoring problems in which there's going to be a different coefficient here other than 1. For example, I'd like the class to do that problem. Well, the only thing you could do here, since 5 only has one factor, that's going to be 5 and 1. You don't have to put the 1. You shouldn't put the 1, in fact. Okay, so that has to go there. Now the only question is this going to be a 3 and that going to be a 1, or is it going to be 5x with, let's say, a 3 here and a 1 here? That's the question. And to figure that out, you have to do this. 1x, 15x. Is there any way 1 and 15 can give you a combination that will give you a 2? And the answer is it doesn't look like it. But if you look over here, 5x times 1 is 5x. 3 times x is 3x. Yeah, that looks like it might give you a 2. So let's get rid of this right over here. And let's try to put this in closer proximity. So let's take what we just did over here and make that 5x and 3 and x and 1. Now let's see what we have. Well, 5x times x will definitely give you 5x squared. 3 times 1 will give you 3. That's good. Now let's figure out the middle term. So this will become 3x. This will become 5x. Right, so let's put the 5x over here. Right, and can we get a 2 out of that? Yes, a positive 2 if the 5 was positive and the 3 were negative. So that would work out because a negative 3 and a positive 5 gives you a positive 2. So that's good. And now the 3 has to be negative and the 5 has to be positive. So let's now check it. 5x times x is 5x squared. 5x times, 3 times 1 is 3. That's good. Now negative 3x, positive 5x would give you a positive 2x. So that checks very, very nicely. And this is the answer to the question. So it takes a little more work when you have a lead coefficient here greater than 1. This was nice and easy because the lead coefficient was 1. That's easy because then it's just a sum and the product thing. But here you have to do a little more work. And in fact, look at this problem. Let's do this together. Because now the lead coefficient is the now that's nice because 2 is the only factor, 2 and 1, right? But now you have to get 12x squared, you could have 12x times x, you could have 6x times x, you could have times 2x, you could have 4x and 3x. Gee, I have all these possibilities. My advice is always go with the middle one first. Always go with the ones that are the closest together, the 4 and the 3. Very rarely is it the 12 and the 1. Occasionally it's the 6 and the 2, but the 4 and the 3 is common. So let's start with that and see how we do. It may not work out. Now we have to figure out a way of getting the 2, so that's easy. It's just going to be either 4x with a 2 here and a 1 there, or 4x with a 1 here and 3x with a 2 there. So let's try all the possibilities. This will give you 6x. This will give you 4x. Well, that's not going to give you 5. No way, right? That's not going to work. See what I'm saying? The 4 times the 1 would give you 4x. The 2 times the 3 would give you 6x. There's no combination here that would give you a 5. So that's not going to work. Let's go over here. So this looks good because 4x times 3x is 12x squared. 2 times 1 is 2. Now let's look at the middle term. This is 3x. This is 8x. And it looks like we can get a 5 out of an 8 and a 3 by subtracting them. Now remember, we want a negative 5, so this has to be negative 8 and positive 3. And that would give you negative 5x. So we want to wind up with the negative 5, and this will do it. This will do it. Okay, but the 3x has to be positive, so that will be positive, and that will be negative. And now let's check ourselves. 4x times 3x is 12x squared, good. 1 times negative 2 is negative 2, good. 1 times 3 is 3x. 4x times 2 is negative 8x. And when you add them, you get negative 5x. So that works very, very nicely. Okay, so you have to, when there's a lead coefficient over here, you have to sort of play around with it. Here's another one to look at. It never gets this, I'll tell you, it never gets this high, but this is a problem I pulled out of the textbook, of the workbook rather. So let's take a look at this, and let's see if we could conquer this. 21b squared minus 13b plus 2, plus 2. Okay, I'll let you play with that for a few minutes. In this situation, it could be 21b. So, this is gonna be either 21 times 1 or 7 times 3. It will be 7 times 3. It's gotta be 7 times 3. Start with that. Don't start with 21. It's 21 and 1. Just start with 7 and 3 and see what happens. Now, let's see if we can get a 13 in the middle somehow. Okay, let's see how we could do this. So, if we put a 2 here and a 1 there, this will give us 6b. This will give us 1b. Excuse me, 7b. Will that work? Well, 6 and 7 is certainly 13, right? So that'll work. And well, they both have to be negative. Because a -6 and a -7 is -13. And actually, a -2 times a -1 is a +2. So that works fine. So we hit it on the first. I didn't, believe me, this was not planned. I just threw in numbers, you know, here and here, and it happened to come out okay. So in other words, 7b times 3b is 21b squared. And 2 times 3 is 6, and 7 times 1 is 7, and that comes out to 13. With this negative and that negative, that works out very, very nicely. And the -2 times the -1 is +2. So this is indeed the answer to the question. If we had done, for example, 7b and 3b and put the 2 here and the 1 there, you see that wouldn't have given us, that would have given us 14b. This would have given us 3b. And there's no way we could have gotten a 13 out of a 14 and a 3. So that wouldn't have worked. But I just happened to get lucky, and this worked out very, very well. Okay, that's called trinomial factoring. And we'll be doing a lot of those as the semester wears on, so you'll get a better feeling for that type of factoring. Okay, so this is, you know, this is the easy kind. This is a little more complicated, and this is very much complicated because you have the extra characteristic of not having, of having a lead coefficient that has multiple factors. Here's the question. What is a perfect square? 36 is a perfect square. Explain to me why that's a perfect square.
Because 6 times 6 equals 36.
And what about 25? Same person.
5 times 5 equals 25.
Very good. You see what's going on here? When
Yep.
you multiply a number times itself, you get a number which is called a perfect square. Okay, so how many perfect squares are there? You know,
Would 1 be a perfect square?
1 would indeed be a perfect square, yes. Let's allow a little more room here, though, because we want to create some kind of list that people can refer to. But, so you're saying 1 times 1 is a perfect square. What else? What comes after 1? 4 is a perfect square. 9 is a perfect square.
Do they have to be whole numbers to be a perfect square? Like, can
Yeah.
you do 0.5, 0.5?
Yeah. Yeah, they have to be a whole number. You have to know some perfect squares. I mean, you don't have to know all of them, but you have to know at least up to 12. You're going to come across perfect squares along the way. In other words, the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. The square root of 49 is 7. The square root of 64. The square root of 81. The square root of 100. The square root of 121. The square root of 144. These are the ones you're supposed to know. The next type of factoring that we're going to look at has to do with this type of situation. Well, let's go backwards as I did in the previous two situations. Multiply x minus 7 times x plus 7 and see what you get. All right, so what did you notice here? What's going on here? Do you get a trinomial when you multiply these two binomials? Ah, very interesting, huh? The middle term drops out. If that's a perfect square, and indeed x squared is a perfect square, and that's a minus sign, this is called a difference of two perfect squares. And in order for that to be a difference of two perfect squares, both of the terms have to be a perfect square, and it has to be a minus in the middle. For example, this is a difference of two perfect squares. What are the factors of x squared minus 25? Write it down. Somebody tell us.
This is Rose, it's x plus 5.
Identify this. Okay, you did, Rose. Go ahead.
X plus 5, x minus 5.
Good. Everybody agree? Anybody disagree? Okay, good. How about everybody factor that one, please? Okay, somebody tell us what the two factors are whose name is not Rose.
This is Talia.
Go ahead.
I think it's negative x plus 8 and x plus 8.
Well, let's keep the terms the way they are. I mean, what you did obviously was to switch them around and make it negative x plus 64. Is that what you did?
I just assumed that since the negative x squared was negative, that one of the x's would be positive and one would be negative.
Well, what you do is you just simply say, what's the square root of 64? And that's 8. And you say, what's the square root of x squared? And that's x. And that's positive and that's negative. That's it. That's all you do. See, it's very easy.
Question.
You understand?
I have a question.
Yes.
What if you did x minus 8 and then x plus 8?
The check, right? I mean, you have to go through the check, make sure you got the right thing here, right? So this is what you wind up with. Is this what the original problem was? Is this what I gave you?
No.
The answer is no. So therefore, this is no good. What you
Okay.
did was you took this and switched it around to make it look more like the one we started with, right? The two we started with. You have to do it the way it is. So just do the problem exactly the way we did it. In other words, take the square root of the first term take the square root of the second term, 1 minus and 1 plus. Take the square root of the first term, the square root of the second term, 1 plus and 1 minus. That's it. Just the way it is. Don't start, changing them around. Try this. Okay, everybody factor that. But once again, do the same thing. The square root of 16, 4. The square root of x squared, x. The square root of 49, 7. The square root of y squared, y. 1 plus, 1 minus. Okay, is that clear to anybody? Does anybody have a question about that? Who's unsure about what happened there? Okay, good. All right, very good. Okay, so that's a difference of two perfect squares. And now we go on to the next type of factoring. So we've come a long way since the very beginning, from greatest common factoring to trinomial factoring to difference of two perfect squares. What could possibly come next, right? Well, hang in there for just 1 minute. So we listed the perfect squares. We listed the perfect squares. Remember that? We had a whole list of the perfect squares. Perfect squares. And, we listed as many as we could think of, 1, 4, 9, 16, 25, and so on, right? And now we're going to take a look at the perfect cubes. See, the line is drawn between intermediate algebra and pre-calculus. What's a perfect cube? 1 is a perfect cube because the cube root, the third root of 1 is 1. The third root of 8. In other words, the number where something times something times something is equal to that number, as opposed to the square root where it's just something times something. Now it's something times something times something. So this is going to be 2. Now, what would be 3? What would go under here in order for that to be 3? Just multiply 3 times 3 times 3. Come on, help me out here.
27.
Good. Yes. 4. That's as far as we're going. We're not going very, very much higher than that. And now we're going to talk about a fourth category of factoring called the difference. Difference. And actually the sum of two perfect cubes. For example, a to the third minus b to the third, or a to the third plus b to the third. Now these are two formulas. These are two formulas. And I'm going to give you the two formulas. Well, I'll tell you how I remember it. I mean, I gotta remember these things, exactly the way you have to remember them. Here's how I remember it. A difference of two perfect cubes starts, see that negative? That negative starts out there as a negative. And then here, it's a positive. This starts out as a positive, therefore that's a positive, and therefore that's a negative. So this is a negative, this is a negative, this is a positive. This is a positive, the sum of two perfect cubes, therefore that's a positive, and that's a negative. Let's take an example. X squared minus 8. Well, follow this very carefully. This, excuse me, not x to the second, x to the third, right? We're talking about cubes now, not squares. Okay, so this would be x to the third minus 2 to the third. Right? That's what we're doing here. Now, using the formula, we start out with x minus 2, because that's minus, and then a squared, so this is x squared, plus ab, well, this is a and this is b, therefore this will be 2x, and then b is equal to 2, and that would be, b is equal to 2, and therefore that will be b squared, positive b squared. So this will be positive 4. So once again, here's the formula. Keep that in mind. Keep the formula in mind. We take this difference of two perfect cubes, write it this way. X to the third, 2 to the third. Take out the x minus 2, just as this tells us. This tells us take out a minus b, but a is equal to x and b is equal to 2, therefore it's x minus 2. And what are we left with? We're left with a squared, but again, since a is equal to x, that'll be x squared. A is equal to x, but b is equal to 2, therefore that'll be 2x, and b is equal to 2, and this is b squared, 2 times 2 is 4. And that this is the answer to the question. This will be a test question on the next test. Let's do a sum. Let's do x to the third plus 1. So first, the way we wrote this, let's write this the same way as x to the third plus 1 to the third. Always write the perfect cube in terms of its factor, right? And now the formula we're using is not going to be this formula, because that's with the negative. We want the formula with the positive. So we look at this formula, and this will be x plus 1 times, now a squared, remember a is equal to x, so this will be x squared. Now that's going to be a minus sign. AB would be 1 times x, which is just x, and then b is equal to 1, remember, and that's b squared, so that'll be 1. And that's what it looks like. It's the same process with the AB and the AB, and the A squared, and the A squared, and the B squared. The only thing is, here, this is negative because that's negative, and if this is negative, that's positive. Everything is the same here, except if this is positive, that's positive, and therefore that's negative. That's how I remember it. And that's called a difference and sum of two perfect cubes. Let's do one more. Let's do one more. Let's do x to the third minus 27, and I'll let you try that. Let's begin. Step one. Write this as x to the third minus 3 to the third. That's the first step. Always write the perfect cube this way and that way, just like we did 8 with a 2. The cube root of 1 was 1. The cube root of 27 is 3. So now we're all set. Now we either use the first formula or the second formula, but obviously we want the one with the negative, so we use the first formula. And this would be x minus 3 times x squared. Now remember, the middle term, when it's negative, is positive. So this would be positive a times b, or in this case, 3 times x. And then plus, because that's plus and that's plus, so that's not a big deal. And then squared is 9, and that's the answer to the question.